In the last two videos, we've looked at modelling the forces acting on a particle. All of our work has been on a horizontal or flat plane. In this video, we're going to look at some basic work with inclined planes. So let's remind ourselves of the forces acting on a particle. So here's my flat plane. Here's my particle. We're going to have now the weight acting down. So the weight acts directly down. Weight is mass times by gravity. We've got a normal reaction force. The normal reaction force is going to be in the opposite direction. It's perpendicular to the plane. So if we had now R, this is the normal reaction force, we had a mass of m kilograms, we'd have a weight acting down of mg newtons. We might have now some forces acting on the particle in the horizontal direction. This might be the tension in a rope. If we had now a rough plane, we might have a frictional force opposing the motion. If we had a smooth plane, obviously we wouldn't have the friction. So what we might have is the frictional force in this direction, we might have T, the tension in the rope, and we might have now an acceleration. So we might be pulling this way, the frictional force would oppose motion, but we'd overcome that and we'd have now an acceleration. And I'm going to call that A meters per second squared. And this was now the forces model, or the model of forces that we saw in the last video. Now let's go ahead and take the particle again. Let's say that the only forces are acting now perpendicular to the plane. So we've got now the weight acting down, we've got the normal reaction force, but we've got nothing in the horizontal plane. Now Newton's first law says that if this is at rest, it will remain at rest until there's a resultant force acting on it. So we can see that this is going to stay in place. So I've got mg and I've got the normal reaction. I could sit here all day and watch this. It's not going to move in this direction. We can see we've got zero acceleration. It's not going to increase in speed from 0 meters per second. In the same way, if it had a constant speed, it wouldn't change. Now, why then, if I took this block, let's take a block, let's put anything, let's put a book on a surface here. Let's say that these are, and we'll just for modelling purposes, we'll say that these are just smooth planes. You might want to think about the good old eel on a Teflon surface or on a slippery surface. Why then, if I put the particle on an inclined plane like so, am I going to collect it at the bottom? Why is it going to sit here and slide down? This right here, this particle on the flat is not moving. But yet, as soon as I put that on there, we know this from an early age. This is fairly intuitive. It's not, you don't need to know this, or you don't need to know mechanics as such to understand this. Let's now look at the forces acting on this particle on now the inclined plane. When we say inclined plane, it simply means that we've got some angle between the horizontal and this plane. It might be the other way around, so you might have something, but let's grab another one up. You might have the orientation that way around. It really doesn't matter, okay? So let's just, let's get rid of that one. So let's put that back. Right, okay. So let's now look at the forces. Now, the normal reaction force is always going to be perpendicular to the plane. So we're going to have now the normal reaction force. That will be like so. So at the moment, we're looking exactly the same. Now, the weight acts directly downwards. Weight is mass times by gravity, and that is going to pull it in this direction just here. So let's say we've got some angle, and this angle we'll call theta, okay? So using the Greek symbol, we'll just have theta. We don't know what it is yet. It might be 30 degrees, 45 degrees, and so on and so forth. Now, what we have here is a mass, and we'll have m. We've got a normal reaction force, and also now we've got the weight acting down, and this is going to be mg newtons. If we look at this, quite clearly, when I spin this round, and what I'm going to do is just now put all of this together. So let's go ahead and group this up. We can see if I turn this round to make now the plane flat, that weight is not going to be now acting directly down. It's acting at an angle. So let's consider what's going to happen. Quite clearly, this particle isn't going to jump through the plane or upwards. It's not going to jump towards the ceiling. There's no vertical acceleration. It's not going to now go through the plane. It's not going to accelerate downwards. So the only movement will be parallel to the plane, or if you like, it's going to be now down the plane. Let's just consider now the angle that we've got. If we've got an angle here of theta, I'm going to put this up, and this is going to now be in line with the normal reaction force. This is in line with the normal reaction force. Therefore, this whole angle is going to be now 90 degrees. Now if I consider the angle down here, and I'll just put this angle here, you might not need to see this, but this may complete the diagram for you. This now is creating a 90-degree right angle. So this is 90, therefore this is 90 minus theta. So all I'm going to do is just take that out away for a second, and we're going to have this angle. Now this one right here is going to be 90 minus theta, therefore this one right here is going to be theta. So we got theta as this now, it's a right angle, and this is going to be 90 minus theta. We're going to rely on some basic trig throughout this. But as we can see now, when I group this back up, let's go ahead and do that. We've got the following scenario. We can see now that I've got some force that's going to be acting parallel to the plane. And that's therefore going to cause me acceleration in this direction. If we've got no other forces acting on the particle, the weight of the particle or the component of that force is going to take it downwards, and that is what gives us our acceleration, and that's what increases the speed from 0 to whatever it hits the bottom with. So this is the scenario that we're going to have, and we'll just say that this is going to be a meters per second squared. So a meters per second squared. Now let's look at this. You might not want to think about this, and this is optional, this is not really convention as such, but what we've got is this scenario here. So I've got now this angle, and this is the weight acting down. So all I'm doing is modelling this on the plane. We can ignore this, let's take this out of the way as it's no longer applicable. We've got now, and we'll put it in fact, we'll put it in the other direction. We've got some acceleration, and this is going to be in this direction. So all I'm doing is now drawing exactly the same model, but on the flat. As stated, general convention is that you just deal with it like so, and after a while you'll see that this is fairly straightforward. So what I've got now is the angle, and the angle just here is going to be theta, okay? So what we'll see is now that this is going to be theta. So this is theta, and this is going to be 90 minus theta. Now you might not want to put this on, as you'll see when we work with trig, you don't always need that. So let's consider the force now of acting in this direction. So what's going to make me accelerate in this direction? So if I just drew this up now, and I'm going to draw this right here, we can consider this in two different ways. We could consider now the force just here, and we've got now the right angle triangle. So here's my right angle triangle. So here now is the 90 degrees. This is the 90 minus theta. So 90 minus theta, and we can say that this is going to be the mg, that's the force. Now if I look and I wanted to work out what's acting parallel to this plane, and I'll put this on, we can see that that's going to be the adjacent of this right angle triangle just here. So I can say now that I'm going to have the following. Acting down the plane, we're going to have now the component of the force, and that is going to be, if I write this on, it's going to be mg, and we're going to have cos of 90 minus theta. Now just think about this, this is basic right angle trig. So the adjacent is going to be the cosine of the angle times by the hypotenuse, and that gives me this orange part right here. Okay, now the cosine of 90 minus theta is the same as the sine of theta. And if you want to see that again slightly different, let me draw another triangle for you. So let me draw the triangle that we've got. So let's go ahead and do that. Let's do that one just there. This time I'm going to model this to be theta, and we're going to consider now the following. So this is theta. I've got now mg. So mg is the hypotenuse of this, and I'm interested now in this force right here, and that's the orange part. Now if we look at this, we've got the sine of the angle this time. So SOH. So if I want the opposite, it's going to be mg. So mg sine of theta. And in general, that's what we use. It is mg cos of 90 minus theta, but using now a trig identity, all we're saying then is these two things are the same. It's fairly straightforward. And if you're not convinced, let's grab a calculator. Let's say that theta was 30. So what we could say then is that if theta is 30, cos now of 90 minus 30 is 60. That's going to give me a half. And we could see that the sine of theta, sine of 30, is going to give me a half as well. So what we're saying here is the following. If I wanted now to express the forces acting on this now, we could say, and the general convention in this particular case is to say that we are resolving down the plane. I kind of don't like the idea of that. I like to say that it's parallel and perpendicular to the plane. So we're resolving now parallel to the plane. If I resolve parallel to the plane, and again this is a notation you might see, or you might see R, I like to say that it's parallel. What we're going to have then is the weight acting down. So consider now the weight acting down. We're looking at this orange force. I want to know what's going now parallel to this plane. And that is going to be mg sine of theta. So that now is the horizontal component of force just here. Now we've got nothing else that's acting on this. So by Newton's second law, using force is equal to ma, as we saw in the last one, this will be equal to the mass multiplied by the acceleration, which is a. At this stage, we can see that this is independent of the mass. We can cancel this off, and I can say now that the acceleration is g, which is 9.8 meters per second squared, multiplied by the sine of theta, and that gives me my acceleration. So all we're doing now is saying, well, that's why we get this now, this movement. We've got this acceleration as we've got the resultant force, and the resultant force means that the particle is going to move from rest and it's going to come down this way. Now, of course, if we had a rough plane, we could consider the forces, and throughout the video that's what we're going to do. But essentially now we want to consider what happens when we resolve parallel and perpendicular to the plane. Now let's go ahead and look at this and say we wanted to find now the normal reaction force. Before we resolved on a model like this, we resolved, and let's look at this one right here. We know we got no vertical acceleration with this, so what we'd say then, using Newton's second law, R minus mg is equal to 0. So we could say that the normal reaction force is going to be mg newtons. And that was something we saw before. Now let's consider what we've got just here. That isn't going to be the case. So when I resolve, and this is going to be perpendicular to the plane, so you might want to show it like that, you might want to say it's perpendicular, or you might even want to, in this case when we're working like so. I'm not as much of a fan of using the notation that we are resolving now in this direction. If I look at it here or look at it here, I want to consider now the weight acting down. Now if I take this arrow right here, if we look at the weight acting down, we've seen that the weight now in the horizontal direction would be mg sine theta. What we've got just here, consider that this is going to be mg cos theta. So when we're resolving perpendicular to the plane, we can say in general R minus mg cos theta, and we'll write this here, cos theta will be equal to 0. So this time R is going to be equal to mg cos theta. So when we're now resolving perpendicular to the plane, we only have this component of the force. Again, if you want to look at that as a right angle triangle, let's look at that as a right angle triangle. We've got the following scenario. We're interested now in what is acting downwards. So if this now is the, let's say that's what our resultant is going to be. This is going to be theta. This is going to be mg. We're interested in what's acting directly downwards. And we can see that if this is a right angle triangle, this is the hypotenuse, this is the adjacent. So we can say now that this is going to be the hypotenuse times by the cosine of the angle. So we can see that that's going to give us that. So in general, when we're resolving, if we've got no other forces, R is equal to mg cos theta. And then if we've got this scenario, we can see that we've got sine theta. So the basic take-home message is, if you've got some angle, let's say that we've got an angle, let's say that this was 45 degrees. What we'd say then, if we wanted now the normal reaction force, we would say that the normal reaction force on this particular case, we could have R, and let's say we've got now, let's say we got a mass of 10. So we've got some particles sitting here. This would be 10g. We could say now that resolving, and this would be perpendicular to the plane, we could say now, and I'll just do it like so, we could have that, or some notation. The notation will differ depending on what you read. We can say R minus mg cos of 45 degrees would be equal to 0. So R is equal to mg cos of 45. The cosine of 45 is 1 over root 2. So using the exact value, 1 over root 2 mg. And that would give us the normal reaction. So let's go ahead and do some work with these. Hopefully that's given you a good idea though of why this is going to now accelerate down the plane. It is the weight, it's the component of weight acting down the plane that's going to take it in that direction. Later on in the video we will look at some of the subtleties in here, but what I want to do is just lay down a brief understanding to see now how this works. Okay, let's model something up. Let's go for now, let's grab this one up. Let's go for a 60-degree angle. So what I'm going to do is have a particle. The particle is going to sit on the plane just here. We're going to have now a 60-degree angle, and that's the angle that it makes now with the horizontal. Again, the terminology on this in these type of questions will differ. So let's pretend, there we go, that'll do. Okay, so what we're going to have is an angle just here. So it'll be making an angle with a horizontal of 60 degrees, and that's going to be like so. Okay, now what we're going to have is a weight acting down. So let's give this a mass. Let's say it's got a mass of 5 kilograms. When we have now the weight acting down, the weight is going to be acting directly downwards. We know gravity acts in this way. So what we've got then is the weight. The weight is mass times gravity. We can write W is equal to mg in general. So W is equal to mg newtons. So this is going to be 5g, and I can put that force on there. We're going to have a normal reaction. Normal reaction is going to be perpendicular to the plane. So what I'm going to have is the following scenario. So we've got this now, and on my diagram to begin with, I'm going to put these on. Later on I'll exclude them, as I'll assume that you're fairly happy. What we're going to do now is have this angle right here, and this angle is going to be 60 degrees. Okay, so what we'll have then is 60 degrees, so let's put that just there, and if you want you can say that's 30. So we've got a 60-degree angle just here. And what we might say then is the following scenario. We might have some acceleration. Let's say the acceleration, we're going to be accelerating in this direction. This is a smooth plane, therefore we don't need to consider friction. And we'll say that this is going to be a meters per second squared. So a meters per second squared, and then we're going to have now a normal reaction force. The normal reaction force is going to be R. So what we've got is this scenario going on. So we're going to be accelerating down here. We've got a mass of 5 kilograms, weight of 5g newtons, this angle of 60 degrees. And I want to find the value now of A, which is acceleration. So let's consider what we've got. If we resolve, and the way you might want to do this, you might want to say that this is going to be parallel to the plane, or you might want to use the notation like so. It's entirely up to you, as long as you're showing the examiner that we're resolving down the plane. If you want, you could draw this up on a flat. So each of these I'm going to draw on flat. As you go on with your work, you might decide, well, actually, I don't really want to do this. And this is, as stated earlier, this is not really general convention. I'm just showing it as if it was on a flat. So what we've got is the following scenario. These are the only forces acting in now parallel to the plane. Quite clearly we've got them acting perpendicular because we've got a normal reaction of a weight. But this is the scenario that we've got. We've got some value that we need to find of A meters per second squared. We've got now a mass of 5. We've got a weight acting down of 5g newtons. And then we've got this angle right here. And this angle is going to be 60 degrees. So this is a pretty steep plane. So if you were standing at the bottom of this and that was a big box or something, you're going to want to move out of the way. That's not going to be enjoyable wearing that by the time it gets down there. So what we're looking for then essentially is now the force acting, and we're looking at this force right here, or if you like, we're looking now at what we're going to get, and that force now is, let's put it like there, that's going to be this just here. This is going to be parallel to the plane. So what I can do is the following. I can now say acting down the plane, and I'm resolving in the direction of motion. I can say that I've got the weight. The weight now is going to be 5g, so this is mg, then we're going to have the sine of 60 degrees. Now let's consider there's no other forces, so I'm just going to put minus 0 here. Now don't need that obviously, all I'm saying is that there's no force acting in the opposite direction. And this is just using Newton's second law. So Newton's second law, resolving down the plane as we saw before. That's going to be equal to the mass times the acceleration. So the mass is going to be 5, and the acceleration is going to now be A. So we can write this as 5g sine of 60 degrees will be equal to 5a. Yet again, we see that this is independent of mass. Dividing through by 5, we've got now g sine of 60 will be equal to the acceleration. The sine of 60 is root 3 over 2, so we can say root 3 over 2 g, and that's going to be meters per second squared is the acceleration, and that's what we call the exact value. So g is 9.8, root 3 over 2, you could just put this in a calculator to get a numeric value. So let's grab that up, and so what we've got then is root 3 over 2. I like to give these as exact answers, but often the general convention in this unit is that you give your answer to 2 or 3 significant figures. So there's acceleration. That's going to be 8.487 meters per second squared. So you are really going to be wearing that if that comes down 5 kilograms. Yeah, 5 kilograms isn't a lot, but if we put an ant there, he's not going to have an enjoyable day. So there we go, we found the acceleration given this information. Now if we wanted to say resolve, let's say we wanted to resolve perpendicular to the plane, now what I could do is use the notation like so. I'm less fond of that. I would just say now resolving perpendicular, Newton's second law, and we could go ahead. So what we're going to have is the following. Resolving now perpendicular, we could find the normal reaction force. We don't need it in this particular case. We've got no acceleration upwards, so we could say now that r, let's write this out, r minus 5g, because we're going in the opposite direction, cosine of 60 will be equal to 0. So r will be equal to 5g cos of 60. Cos of 60 is going to give us 1/2. That's a nice value. So we can say that r will be 5 over 2g, or 2.5g newtons. So all I've done is gone ahead and found that. Okay, let's look at another scenario. Let's do something else. Let's say we've got, let's go for something slightly flatter and shallower. Let's say I've got this. Again, we'll stick with a smooth surface. So with a smooth surface, we can now discount friction. So you'll be given in the question, it will say smooth. Okay, so you'll be told, or you'll be told that there's friction acting on it. So this is smooth. Now let's say that I'm somewhere on here, and again I'm trying to push a sledge up this hill. So pretend that the contact between the two is perfect. It's got now a coefficient of friction of 0. And again, we looked at the coefficient of friction before. So what we're going to have is the weight acting downwards, and that's going to be acting directly downwards. We've got now this normal reaction force, and that's perpendicular to the plane. So perpendicular will do something like that, and then we will have that. Okay. Now I'm going to apply some force. So there is little me, the other side of this, pushing with all my might. And let's say that that's some force. Let's say that that's P. Now I could put this the other side. I'm modelling this now as a pushing force. I could quite easily model it as a pulling force. It really doesn't matter. All we're doing is essentially saying that we are going in this direction. Now let's say I'm being hardcore one day and I'm getting this thing to move. I'm holding back and I'm thinking, no, I'm feeling pretty strong. And I'm going to accelerate this in this direction right here. So we could say that this would be, say, 2 meters per second squared. So we're going to look at another scenario. Now with these scenarios, I'm not going to cover everything, but hopefully it will give you some idea of these. Let's say I really want to give this a massive mass, but let's just say make working easy, that's going to be 10. So we're going to have 10 g newtons, that's the weight acting down, and let's say that this is going to be now r. That's a normal reaction. Let's give myself an angle more realistic, well, slightly more realistic than 60. Let's go for 30 degrees. 30 degrees is nice and straightforward to work with, and we can see then that we're going to have this angle right here. This angle in here is also going to be 30. So let's put that up perpendicular to the plane. So we've got this angle just here, which is going to be 30. Now I might be asked to find the value of P, okay? So let's go ahead and look at finding the value of P. Now, the last two scenarios, I haven't bothered looking at the normal reaction force. I'm just considering these forces right here. So if we wanted to draw this up, if you wanted to still draw this on a flat plane, let's consider the forces acting on this. We've got now force, and if you wish, we can put P in this direction. P is going in that direction. I'm accelerating it now in this direction, and then I've got the weight acting downwards. Now the weight acting downwards is going to be in this direction. So what we've got is the following scenario. So if you wanted to sort of turn this round and sort of look at it in this way, this is what you're going to see. And let's go ahead and put that on. Let's do that. And this is going to give us an angle now, and that's going to be 30 degrees. So let's consider what we've got. We've got now a mass of 10, so that's going to be 10. The weight acting down is going to be 10 g newtons, okay? 10 g newtons, 30 degree angle. we've got to now, this is going to be parallel. So when we're looking at the horizontal and vertical components of this force, it's purely horizontal, and that's purely P. So 2 meters per second squared. So as you can see from this forces diagram, the only thing we need to solve for is P. So let's use Newton's second law, and we could say if we took this model, we're resolving up the plane. So resolving up the plane, we'd have the following. Consider now P, then we're going to have the component of weight acting down. And again, we can split this into the vertical and the horizontal, and this is going to be, and even if you want to do it like so, even if you want to put it here, I'm looking now at this force right here. We've got the hypotenuse. The hypotenuse is 10g. We've got the angle 30. So this side of the right angle triangle is just going to be 10g sine 30. So acting down the plane, which is the weight here, mg, we've got now 10g sine of 30 degrees. Now, using Newton's second law again, remember this is just F is equal to ma. I'm resolving in the direction of motion. P minus 10g sine 30 will be equal to the mass, which is 10, multiplied by the acceleration, which is 2. Okay, so let's look at that. Now, sine of 30 is a half, so P minus 5g will be equal to 20. So P will be equal to 20 plus 5g. G is 9.8. 5 times 9.8 is going to be 49. So we can see from here, just adding that up, the force I'm exerting now is going to be 69 newtons. So we've solved for P. Okay? So nice and straightforward, nice and logical. All I've said to myself is now, if I want to accelerate this at 2 meters per second squared and the weight is acting down at this angle now, we're going to have the scenario where I've got to push with a 69 Newton force. So there I am, little old me, pushing up the plane, and we're getting this P, which is going to be 69 Newtons. Okay, let's switch things up. So far we've been having it easy. We've been having a smooth plane. Let's go ahead and look at a rough plane. So you'll be told that it's a rough plane, or you'll be told that there's friction. Let's model 30 again. 30 is a nice number to work with. All of these are because they're exact values. If you haven't met exact values yet, you will do later in your study. But the sine of 30, cosine of 30, sine of 60, sine, cosine of 60, 45 are all nice numbers to work with as exact values. So what I'm going to have this time, I'm going to say I'm going to have a rough plane. So let's say this is rough. Okay, so rough, and we're going to have now a coefficient of friction. We looked at the coefficient of friction. That's going to be 1/2. Let's say it's 1/2. So mu is going to be 1/2. Let's now add on some information. Let's just say, I don't know, let's say that this is going to be, we'll give this again a mass of 10 kilograms. Make our life easy. Just to model these up. So this will be 10 kilograms. Normal reaction force is always perpendicular at right angles to the plane. Okay, so it's going to be something like so. So let's say that this is going to be 30 degrees again. So this will be 30 degrees. 10 is the mass, 10 kilograms. Weight is mass times gravity. So if you want to write, W is equal to mg newtons. We've got now 10g. Now what I'm going to do is pull this. I'm going to stand with a rope this time. Okay, so my rope is going to be, let's say that we've got this, let's put a rope now, and the rope is going to be parallel to the plane. Now, it might not always be. We've seen before that it's not always the case, and that's not a problem. We've just got to resolve, now it's vertical and horizontal components, that's not an issue. So let's say now we've got friction. Now friction is going to be opposing the motion, and you could of course model friction here. You could say now that's opposing the motion. I like to put it the other side. I think it's slightly easier to see. But do expect some texts or exams might have the friction pushing in this direction. Now what I'm going to do is model F. F is going to be just here. We're going to have T, the tension, right here. Now what I'm going to do is find the value of T. So I'm going to need an acceleration, so let's put an acceleration. Let's say again I'm being pretty strong. So this time it's not yanking me down the plane, I'm actually pulling it this way. And let's just give this a value. Let's say that again, let's go for 2 meters per second squared. Let's make our life easy. 2 meters per second squared. We've got a rough plane. Normal reaction force now, and we'll consider the following. So we got T, this is some force I'm pulling with. We've got frictional force opposing the motion. Frictional force is always going to be opposing the motion. Now if I got acceleration, we've got now frictional force is equal to mu r. It's now limiting, and we saw that before. So what we can say then is F max. We've got the frictional max. Because I've got acceleration, this is as hard as it can go. It can't take any more. Therefore, we're overcoming the frictional force. Now let's go ahead and look at this. What I can do just here, the first thing now is to find r. If I consider now resolving, and what we'll do, let's go ahead and grab that up. We're going to resolve perpendicular to the plane. So resolving perpendicular to the plane is going to be resolving upwards. Now if I consider that there's no vertical acceleration, so I'm not shooting off towards the stars and I'm not plummeting through the plane. If we resolve upwards, and I like to say perpendicular, we're going upwards now, what we're going to have is the following. We're going to have r minus, and this, remember, is a 30-degree angle. We're going to have minus 10g cos of 30 degrees will be equal to 0. That's Newton's second law. F is equal to ma. So we're resolving now perpendicular to the plane. So from here I can see that r is going to be 10g cos of 30 degrees. Cos of 30 degrees is root 3 over 2. So I could, if I wanted, write this now as r is going to be 5 root 3 g newtons, and that's an exact value. When you're working with these, you can leave them as sines and cosines, especially if they're not exact. Don't go and butcher it straight off. Leave it now. Don't truncate the answer. Leave it as the exact answer. So I can see now that my normal reaction force is going to be root 3 multiplied by 5 multiplied by g. G is just 9.8 meters per second squared. So what I can do now is see that the value of the frictional force is going to be the product of these two things. So I can write now, therefore, we can say friction is equal to mu r, and you need to make this distinction. Now we know in general that the frictional force is at most mu r. This though is limiting, therefore it's at its maximum. I've stated that to whoever's reading this, so we can say that frictional force is equal to mu r. So the frictional force is going to be r, which is 5 root 3g multiplied by mu. So let's go ahead and put that in, 1/2, then we're going to have now 5 root 3g. So the frictional force as an exact value, frictional force is going to be 5 root 3g over 2 newtons. And I'm just going to leave that alone. Now all I've done is resolve perpendicular to a plane. Again, if you wanted to see this on a flat, so if you wanted to spin your head round, essentially what we've got here is the particle. We've got the normal reaction force. We've got now the weight acting down. So the weight acting down is going to be at a 30-degree angle with now that perpendicular. So there's your 30-degree angle. We've got these two forces, and these two forces, and this isn't always the case, are going to be parallel to the plane. So all I'm going to do now is consider resolving. Now often this is where students miss out information. So all I've done now is put this on. This is going to be the 30 degrees, 10g newtons acting down. We've got now the tension here, we've got the normal reaction which we found, and then we've got the frictional force. Now we can see at this stage that the frictional force is actually this value right here. So if I put that on, we've got 5 root 3 over 2g. Now we know acceleration is going to be 2 meters per second squared. So what I'm going to say is resolving parallel to the plane, or like so, or if you wish, you could, if you really wanted, you could say up the plane. The general convention is that we resolve in the direction of the motion. So what we've got then, using Newton's second law, so NTL, Newton's second law, we've got T. Now be very careful here. We've got now minus the frictional force. This isn't in the direction of motion. We've got acceleration in this way. If the acceleration was in the other way, we'd have F now minus T. But we've got T minus the frictional force, which we found to be 5 root 3 over 2g newtons. Now at this stage you might still be calling it frictional force, and you might substitute that later. And that will be the case especially if you're trying to find two unknowns. Now this is where we need to be careful. We also have the component of the force acting down the plane, and that's going to be minus 10g, and we're going to have on here sine of 30 degrees. So yes, I'm coming in this direction with the frictional force. That's opposing motion, that's acting down the plane. But I've also got the weight acting down the plane. So if you like, you can consider this additional force with the orange arrow to be the force right here. That is there. That is the weight acting down the plane. So we've actually got two forces opposing the motion. Now this is going to be equal to the mass times the acceleration. So that's going to be equal to the mass, which I've defined to be 10, multiplied by the acceleration, which I gave as a value of 2 meters per second squared. So what we can do here is just go ahead and solve for t. So let's make t the subject of the equation. T will be equal to That's going to give me 20. Let's write it as 20 rather than 10. Plus now 10g sine of 30. So 10g sine of 30. And then we're going to have now plus the 5 root 3 over 2g newtons. So we could, of course, tidy this up. We got t is equal to 20. So that's now my 20. Now sine of 30 is a half, so that's plus 5g. Plus now 5 root 3 over 2g. And that now, whatever numeric value that is the tension that is in the rope. That's what I'm pulling with. So if you wanted a numeric value, again, you could do a lot of factoring with that. But if we had 20 plus now 5g is going to be 49, so plus 49, plus now 49, let's put this is a bit messy. As you can see, that I could do a lot of factoring. I'm giving 5g to be 49. G is 9.8, 5 lots of that. So this is going to give me the value that that's going to be a force of 100, and we'll do that to 3 significant figures. T is going to be 111 newtons. So that's what I'd be yanking up the plane with my rope. So this time the force is acting parallel to the plane, and all we're doing is trying to combat now the friction. We're trying to overcome friction. Friction is always going to be opposing the motion, and we're also battling against the weight. The weight is gagging to take the thing down this direction, but we want to move, and we're being strong, and we're now getting an acceleration in the correct direction. So that's what I need to exert for this now to have an acceleration of 2. Now if it did have an acceleration of 0, these forces would be balanced. So if it was 0, if we said it was in equilibrium, it wasn't either moving or it was moving with a constant speed, we could simply say now that t minus 10g sine of 30 minus the frictional force must be equal to 0. So this is if it was in equilibrium. So I was pulling, it was pulling, and we have this scenario. We would say the following, we'd have this, and we'd just go ahead and solve. Okay, let's move on and look at one more scenario. Let's make something slightly more challenging. Let's go ahead and crank up, let's say we've got a 45-degree angle. So that looks more like 45 degrees, and we'll make this a bit bigger. Okay, what I'm going to do is put a particle on the plane. Now, before we have these forces, okay, and I applied the forces parallel and perpendicular to the plane, or in general, we have these parallel forces. What I'm now going to do is have a force that is going to be parallel now to the ground. So this time, it's not here parallel to the plane, it's parallel to the ground. And let's just give this a value. Let's make up a value. Let's say that's a 10 Newton force. Let's just say this is 10 newtons. It might be inaccurate, but we'll worry about that later. Let's go ahead and put some of these on. So what we'll have the weight acting down. The weight is going to be acting down here. Normal reaction force, perpendicular to plane. That will be in that direction right here. So let's say that we've got now a mass of 20 kilograms. So if we've got a mass of 20, let's put 20. We've got now a weight of 20g newtons. We've got now normal reaction force. And I'm going to say that this is going to be rough. So let's go ahead and say that this is rough. Okay, and we'll be told now that the coefficient of friction is going to be equal to mu. So coefficient of friction is equal to mu, and we need to solve for mu. So let's put some information on here. Let's say, again, let's make our life a lot easier. As I'm kind of making these up as I go, I'll make things slightly easier. Let's say we've got 2 meters per second squared. So 2 meters per second squared again. And then we've got an angle. Let's put this angle. Let's say this is 45 degrees. Again, the sine of 45 degrees and cosine of 45 degrees are straightforward to work out. In fact, while we're here, let's say we were given a plane now and we had alpha. Okay, let's say that we had alpha just here. And we had now that this was 5 and this was going to be 4. This is a Pythagorean triple, so we could write now that cos alpha, and you won't always be given these, you'll just be given alpha. You could say that cos alpha was the adjacent over hypotenuse, which is 4 over 5. We would spot this to be a 3, 4, 5 triangle, and we could say that the sine of alpha, so sine alpha is going to be 3 over 5. And if you wanted tan alpha, so tan alpha would be equal to 3 over 4. So when you're dealing with this, and I'll show you as a sub the value of sine and cosine of 45 in, often you're given this scenario and you just work with these. In a later video we will look at that to see those values, but it's not something that you should be scared of. Let's go ahead and put that there. So we've got now 45 degree angle. Now this, I'm going to say that this is going to be a rough plane. So we've got a rough plane, so this is 45. And we're going to therefore have a frictional force. Frictional force is going to be opposing the motion. So if I'm pushing up, what we'll have now is the following. I'm pushing up, we're saying that it's accelerating this way, so the frictional force will be acting in this direction. Now, if it was accelerating in the other direction, then we'd turn frictional force around. And again, we'll look at examples of where that happens. So I'm going to model friction force as opposing the motion. I'm telling myself, or the listener, or the viewer, that now we're going to have some scenario where we're accelerating in this direction. So here's my frictional force. I've got now the weight acting down. I've got normal reaction force, and I've got now to find the coefficient of friction, which is mu. And this is quite a tough problem. Now, if you want to look at this like so, this is the issue here. But if we look at this and actually put this on a flat, so if you turned your head round, what you'd actually see is that this force right here is acting at a 45-degree angle. And all it is just here. Now, if you want to look at it like so, just go back to alternate angles at school, or Z angles. This is 45 degrees. These are parallel. This force is parallel with this one. So that's 45 degrees. So straight away, I can make my life easy and just say, well, actually, that's a 45-degree angle there. This is going to be 10. That's 10 newtons. We've got now the other forces acting on this. Now, if we look at the following, let's just draw this up. So again, this is me taking this as a side view. Okay. So there's my normal reaction force. Normal reaction force, 20 G newtons acting down, that's the weight. So this then is going to be here. And we know that this angle right here, let's spin this round, let's get this there. This angle is going to be a 45-degree right angle. 45-degree right angle, that's a new thing, 45-degree angle. I should really say that that is a right angle. Hopefully you can see what I mean. I think after 41 and a few minutes I'm allowed to make the odd slip. So there's, right, let's go for 20G. So that's 20, normal reaction, so this is going to be R. Now let's consider the other forces acting on this. I could put this here, this is a frictional force. If you want to put it there, or if you want to put it there, I just like to put it here because it's kind of, we're going in this direction with these two forces, and we're going in this direction right here. So what we've got then is this frictional force. That's going to be opposing the motion, and it's going to be limiting again, because F is going to be equal to mu r as we've got acceleration. And I'm saying again, I'm accelerating this up now the plane, and we need to find the coefficient of friction. How accurate this model is up for debate, but we'll give it a go anyway. Let's see what we're going to have. Let's go ahead and work out this. In fact, let's increase this. Let's make this 100. Let's go ahead and make this a bit better. Let's say we got 100 newtons on that. In fact, let's really push it out. Let's change this over. Let's make this now a force. Let's look at something that's realistically going to work. Let's say let's say that we got a 300 Newton force. So let's really crank that up. 300 Newton force. 10 is not going to do the trick. So let's put that there. Let's go for 300. Okay. So let's look at what we've got. We've got 300 newtons there. And this again is an angle. Just consider that this angle right here, using your basic knowledge, that's going to be 45 degrees. So what we've got then is the acceleration. I've defined the acceleration. What did I choose? 2 meters per second squared. Right, okay. Now at this stage, we've got to find the coefficient of friction. Now let's see what we've got. We know that the coefficient of friction is going to be found by dividing F by R. If we look now, we can say that F is going to be equal to mu R. Okay, we can say that this is limiting. We can say now that we've got F max. So we've got F max right here. Now let's go ahead and resolve. Now I'm going to look at this as the model, but of course we could look at this. We can say that I'm going to resolve perpendicular to the plane. Okay, so if I resolve perpendicular to the plane, we need to be careful here. We've got all of these forces. So the normal reaction force minus, now this is just Newton's second law, okay, so Newton's second law. Let's look at this one. We've got this weight acting down here. Now we've seen before that the weight acting down is going to be 20g cos of 45 degrees. Now if we consider this weight acting down here, this is going to be, the force is going to be acting in this direction. That's going to be minus 300 newtons multiplied by the sine of 45 degrees. Just have a look at what we've got here, okay? This is just a little right angle triangle. If I draw this up to the side, let's look at that. So what we want then is how much of this force is pushing in the direction downwards. And if we look at it now, we've got 300 on the hypotenuse. We want to know this component right here. There's my right angle. This is 45 degrees. So we can see this is the opposite. This is the hypotenuse. So if I want the opposite, it's the sine of the angle. So sine of 45 multiplied by 300. Now that's going to be equal to 0. These are all of the forces and there's no vertical acceleration. So all we'd say then is R is equal to 300 sine of 45 degrees and then plus now 20g cos of 45 degrees. So that's what I've got right there. So that's my value of R. And I'm going to come back to that. Okay, so that's a numeric value. Now let's consider what we've got just here. Now if I've got R, so essentially what we can do is look and use this, but what I've got is a frictional force here. So let's resolve now parallel to the plane. If you like, you resolve it. And at this stage you might want to say I'm going to be resolving up the plane in the same way I've just resolved now perpendicular to the plane. Okay, so let's go ahead and do that. Let's move in this direction right here. So what we've got is the following. We've got now the horizontal component of this force. I want to know how much is going there, and that's this side of the right angle triangle. So I can say that I've got 300, so I've got 300 cos of 45. Now what's opposing that? Well, that's going to be the weight. So I've got the weight just here, and that's going to be now 20g, and that's going to be the sine of 45 degrees. That's now the weight acting down the plane. Minus the frictional force, and I'm going to put here, now at this stage I'm going to put frictional force, and that will be equal to the mass, which is 20, multiplied by the acceleration, which is going to be 2. Okay, let's go ahead and look at this right here. So what we've got then is the following. Let's do a bit of rearranging. Let's make F the subject. So on the right hand side we're going to have F, and that's going to be now 300 cos of 45, so 300 cos of 45, minus 20g sine of 45, minus now 40. That's this right here, and that's going to be equal to the frictional force. Now at this stage you could tidy this up. We could write the cosine of 45 and the sine of 45. These are the same values. It's either 1 over root 2, or if you rationalise it now, root 2 over 2. Whatever you do though, don't sort of mess this up just to do this. So this is going to be 150 root 2. This is going to be now minus 10g root 2. All I'm doing is putting that there. Minus the 40 is equal to the frictional force. Now we know that that's going to be mu multiplied now by r. And this is r, so I'm going to sub this in. So 300 sine of 45. It's general convention that we would leave it in this form. And I might even just put it back in that form. Sine of 45 plus now 20g cos of 45. So that is what we have. So if I put this in a calculator now, dividing through, if I wrote it back like so, I'd have 300 cos of 45 minus 20g sine of 45 minus the 40 divided by the content of that bracket just here, which is going to be 300 sine of 45 plus 20g, remember g is just 9.8 meters per second squared, cos of 45. So cos of 45 will be equal to mu, the coefficient of friction. And we met the coefficient of friction before. We've seen that that's in general between 0 and 1. So let's go ahead and do this. Let's go put this through a calculator. So let's find the value of mu. So we've got now 300. So let's do 300, and then we're going to have now the cos of 45. So cos of 45. Again, if you simplify this, make it clear to the examiner what you're doing. Minus now 20g. So 20 times 9.8 times by the sine of 45. Okay, and again, you don't need your multiplication there. And then we're going to subtract away from that now 40. And we'll put this now over, what have we got? 300. So 300 sine of 45. And then we'll add this now to, let's put another bracket on, plus now 20g. So 20 times 9.8 times by cosine of 45. And we will get our coefficient of friction. So coefficient of friction, That's pretty small, 0.095 and so on and so forth. So let's say that that's going to, and I'll do that to 3 significant figures. So what we're going to have 956, 0.0956. That's pretty slippery, and that's mu. So with this example, I've kind of been making the numbers up such that it's not a brilliant representation, but hopefully that'll give you some idea on resolving the forces. So this time we've had this one right here. Now you didn't have to do that. You could have taken out the point just here and you could have worked around that, but that's just one way of doing it. Ultimately, will you be doing that? My answer is probably not. You'll probably just spot this and just take the horizontal and vertical components of force. But hopefully now that has given you an idea. I'm hoping just here that my values are correct. If not, just go with the flow. Just go with the method rather than what I've actually done. So there we go. That's a basic introduction. So we're looking now at dealing with forces acting on particles when they're on a plane. So they're not on the flat. We've looked at rough planes. We've looked at smooth planes. We've looked now at the coefficient of friction and just a range of different problems. In a later video, we'll look at some of the subtleties. So we'll look at the consequences of tan theta and its relationship with mu as whether something is going to slide or not. But for now, basic introduction to inclined planes.